Today we're going to take a look at section 3.2, and 3.2 is coming right on the tail end of the test that you just talked on the last one, where the last page we talked about some maximum and minimum value issues. So we're going to hit on a little bit more of that today. The first thing I want to talk about is something called a relative or a local extrema. Relative and local are used interchangeably in different textbooks. They mean the same thing. All a relative or a local extrema is it's a point on the interval where it's a maximum or minimum value. It says to notice that the derivative at this point is either 0 or it doesn't exist. So let me draw sort of a picture or a potential picture of what could be going on here. This is a very familiar graph to you. This is a cubic graph. And on this cubic graph, there are two locations where it has a derivative of 0, right? Right here at the top, that peak, and then right here, hang on, at the bottom, this valley. Those are called local or relative extreme points. Now you notice the first one that I marked, and I'll circle it here in green, it's not the biggest y value on the whole graph, is it? No. Because if you go over here to the far right, this definitely keeps going up forever. I mean, that's what the picture's showing. So that point that I circled in green is not the absolute biggest y value. However, in a small area surrounding it, it is the largest one. It is a local maximum. Okay? Same thing for this point here. It is a local or a relative minimum. And I always like to give the example of my family. So some of you have stood up here beside me before, and you know how tall I am. You know how tall I am, right? I mean, like, roughly speaking. I will tell you that my mother says that I'm tall. Jason, am I tall? No, I'm not tall. At least I would say I'm not tall. However, my mom's perspective is that I am because she's 5'2", okay? And my sister's 5'2", and my grandmother was 5'1", and I'm the tallest female in my family, and I'm 5'4". So my mom thinks I'm tall. So this was quite the shock when she came up to visit us the first fall that we were living in Ohio, and we were youth pastors. And every child in the youth group was taller than I was. And I'm telling her I am not tall. But it's all about who you're comparing, right? You're being tall or you're being short. It has to do with the comparison of who are you trying. I would say that Blaine is tall. How tall are you, Blaine? 6'5". 6'5". But if you go out and you play with the Thunder basketball players, are you going to be considered tall? No, you're not. It's all about who you're comparing yourself to. It's a relative term, okay? So these are relative or local extreme values. That's what we're talking about here. Oh, one more point. You can find these when they have a location where there's a derivative of 0, like these were. But you can also talk about them being a derivative that doesn't exist. In other words, it could look something like this. So this particular derivative doesn't exist, but it's still a relative maximum value. Make sense? So this term is not talking about whether it has a derivative or not. That's an independent description of whether it has or doesn't have a derivative. All right, so these locations, however, where we find these relative extreme values all come from things called critical numbers. Critical numbers are simply all of the locations where either the derivative is 0 or the derivative doesn't exist. So the way that we find these extreme values is by finding all the places where we might have them happen. Now, sometimes when we do that, it doesn't work out. So I've got one on the board, and I'll draw it again on here so it's on the video. If we take a look at this equation right here, we have a location where we have a derivative of 0. It's right here at x equals 0. However, so this would be considered a critical value, right? So x equals 0, because when I take the derivative, it's equal to 0 when x is equal to 0. This is a critical number. So you kind of think of it, critical numbers, as being the potential places. The places where I have to check it out and make sure. Right? It's the child that comes home that says just enough truth that makes you wonder if the whole story's true. And so you have to figure it out. These are places where we might have a relative extreme point. So we call them critical numbers. And so when we're finding our critical numbers, or when we're finding our relative extrema, we start by finding critical numbers. Okay? So we're going to start with a function that's a very simple function, polynomial. You guys know how to take the derivative of this just fine. And the directions say we're going to find the critical numbers by hand. And then we're going to use our knowledge of the type of graph it is to determine if it's a local max, a local min, or neither. All right, so when we're finding critical numbers, what we're doing is we're finding locations where the derivative is either equal to 0 or where the derivative doesn't exist. That's what we're doing. So we start by finding a derivative. So somebody tell me, what is the derivative of x cubed minus 3x squared? 3x squared minus 6x. Does everybody agree? Okay, so we find the derivative, and we find out, okay, well, where does that derivative either equal 0 or doesn't exist? Now, on this one, it always exists everywhere. Why? It's a polynomial. Yeah. So this is a polynomial. I don't have to do the where does it not exist step. All I have to do is find out where is it equal to 0. How do I find out where this thing is equal to 0? I factor. And we could factor out an x, or we could even factor out a 3x, couldn't we? Yeah. 3x would be maybe a little bit more thorough, I guess, but either way would work. If I factor out a 3x, I get x minus 2 left. And then I set each of these equal to 0. And I get two possible critical values, x equals 0 and x equal to 2. So these are my critical values. Everybody good so far? Now these may be maximums, they may be minimums, they may be nothing. But they are my possible spots to test. And they're the only possible spots to test. I have no other options. It's either one of these or none of these. I mean, these are only options. All right, so how do we test whether it's a local max or min? Well, this particular problem says to use your knowledge of the type of graph. This is an x cubed graph. So x cubed graphs, we talk about maybe calling it end behavior. The far ends of the graphs do one of two things. They either go down on the left and up on the right, or they go up on the left and down on the right. Those are the only two options. They may do some various things in between. They may have some peaks and valleys, or they may not. But in terms of the end behavior, what happens on the ends of the graphs, it does one of these two things. Which one does this one do? The first one. How come? Right. And what is positive? Nope, it's not about tangent lines yet. The x cubed. The x cubed itself tells us which of these two pictures happen. Because the x cubed is a positive, right, it has a coefficient of positive 1, this right here is the picture of what I have going on. Okay? I'm going to draw this picture a little bit more thoroughly, since I know that's the one I want now. So I know the picture goes down on the left and up on the right, because the x value, the x cubed value, is positive. Now, in particular, in between, this means that I've got this going on, because I have to have two locations that have slopes of 0. Are you guys with me? Now think for a moment here. I'm going to put these on an xy axis. Actually, I'm not. I'm going to take that back. I'm just going to put the x-axis down below. There are two locations here where I have slopes of 0, right? And they correspond to these two critical values. That first one, right here, is that one x equals 0 or x equals to 2? It's 0. Why?
Because the closest one of this guy, I mean,
Right.
2 is positive.
Because we're just putting, it's a number line, right? It's just in order. So this is the x value of 0, and this is the x value of 2. I'm not trying to trip you up or anything, but I want you to recognize something that's going to happen here. X equals 0 then, is it the local minimum or the local maximum? It's a local maximum, isn't it? And x equals 2 is a local minimum. So the x value itself does not tell you whether or not you've a max or a minimum. Right? Obviously 0 is smaller than 2, but 0 here's the maximum and 2 is the minimum. Because we're not talking about the x value, we're talking about the y value being a higher or lower value. And really, even, we're not talking about it in comparison to one another. We're talking about it in comparison to the points that it's nearby. And really, 0 and 2 aren't even nearby each other in terms of looking at the picture of this graph. Now, this is all the answer is right here. So let me write this out. So we have a local max at x equals 0. And we have a local min at x equal to 2. Sorry, that's on the top instead of the bottom, but that's where I've got space still. So this is my actual solution up here in this box. Keep in mind that this asked for critical numbers, which means that what I just wrote down is sufficient. If it said a critical point, it would mean that you wanted an xy ordered pair. Could you find that? Sure. What would you do to find the y value that corresponds to x equals 0? Plug in 0 where? To the original equation, yeah. So if we actually wanted to sort of flesh this out a little bit more, describe this a little bit better, we could actually look at this and we could say, oh, look, if x equals 0, we actually get y equal to 0. So the ordered pair is 0, 0 up here, right? We've got a local maximum at 0, 0. And if we take a look at then if x is equal to 2, can you figure out real quickly what the y value is? It's not 0. It's -4, yeah. So this is at the point 2, -4. Now I want you to notice this is interesting because I'm about to mess it up in the next example. But if you take a look at this one and you actually compare to these, because this is a smooth and continuous graph, you notice that the maximum and the minimum here makes sense, right? This maximum of x or y equals 0 is bigger than this minimum of y equals 4. That sort of is a picture view of what you're seeing, and that sort of makes sense that that's what's happening.
Can you repeat how you know it was that graph versus the other one where it started up and went down?
Yeah, the coefficient in front of x cubed tells us. If it's a positive coefficient, this is the picture you have. If you had a negative coefficient, in essence, it would flip upside down.
Okay.
Or you could say it would flip around left, right. Yeah, it's the coefficient in front of x cubed. Okay, let's take a look at another one. You'll notice one difference in the directions. What's different in the directions here than on the problem we just did? Yeah, so on this one, they're saying you may or may not be able to sort of flesh out this in your mind. X cubed is not a difficult graph to remember pieces about, but even if it were, you have another option. You could be looking at a graphing calculator and actually make some of these assessments too. Does that make sense? So I don't really care which of those two directions you follow. Some of them have one of these directions, some of them have the other one. I just wanted to show you that you could think about it from both ways. The first part's the same, though. It says find the critical numbers by hand. And finding critical numbers means doing what? Finding a derivative and then setting it equal to 0. Or setting it equal to where it doesn't exist, right? All right, so let's find this derivative. This is a little bit more challenging one to find a derivative of because it's a quotient, right? Okay, so somebody tell me, what do I do first in my quotient rule? All right, the denominator, good. And then what? Derivative of the top, which is 2x, great. Got subtraction, now what? Right at the top, which is 1, good. And excellent. I think you guys are getting the hang of derivatives. All right, so let's simplify the numerator of this. I've got 2x squared plus 4x minus x squared plus 2. Did I get all the pieces of that right? Okay. Now that numerator will simplify one more time. What will it become? Mm-hmm. All right, so tell me something you're seeing on this one. What do you notice? I'm trying to make that a better plus sign. I'm not having any success, so I'm just going to leave it.
X plus 2 stuff squared, isn't that, once you FOIL that out, you flip it in the numerator?
Okay, so if we compare the numerator and the denominator, they're not the same thing, right? The denominator, if we were to FOIL it out, we would actually get something very similar to the numerator, but it wouldn't exactly match. And in particular, another way we could think about that, opposite of the way you just said it, Ben, is that if we looked at the numerator, we could factor, right? Or at least we could attempt to do so. What happens if we attempt to factor that numerator? Things get crazy. That's a very good description. It doesn't factor, actually, right? All right, so now you're back in Algebra 2 in high school. Maybe a college algebra course where you encountered this again at another time. What do you do when something doesn't factor? Quadratic formula. You could also do completing the square. That would be another option, but quadratic formula is usually people's default on this. So before I go to the quadratic formula, let me make one more comment about that denominator. What would happen if the denominator equals 0? I would get an asymptote or a whole. I mean, those are the two different things. There's actually going to be an example in your homework where you don't get an asymptote or a whole, you get a sharp turn. We actually haven't seen one happen like that yet, but you're going to get one in your homework. So we do have that possibility as well. On this one, we don't have that possibility. It's a weird one in your homework when that happens, and you'll notice it when you get there. But yeah, it's an asymptote or a whole. Which one's this one? It's an asymptote. Right. We get wholes when we're able to factor and reduce. We don't have any reducing that we can do in this one because we've noticed that the numerator doesn't factor. So one of the two things, my goal is, remember, to find critical numbers. Critical numbers mean finding where the derivative is 0. That's going to be found by using the numerator equal to 0 in the quadratic formula. Or where the derivative doesn't exist. And the derivative here is not going to exist when the denominator is 0, right? So we actually have a location here where f prime of x doesn't exist. And it doesn't exist when the denominator equals 0. What value will the denominator equal 0? Negative 2. However, this is not a local max or a min because what is it? It's an asymptote. So I'm going to write down that we sort of visually checked this or thought through it. But it is not a maximum or minimum value. Did it stand the chance of being one? Absolutely. But we've got an asymptote here from what we know about this type of a function. So we've sort of dealt with the issue and now we're done with it. We don't have to talk about the asymptote issue again. We do have to take that numerator, however, and set it equal to 0. So now we're going to look at where the derivative equals 0, which is where the numerator x squared plus 4x plus 2 equals to 0.
So that does not exist.
The derivative does not exist where the asymptote is. So that the first piece that we did up there, f prime of x equals does not exist. We found out that the derivative does not exist at x equals negative 2. But the reason is because there's an asymptote there. And if you have an asymptote, you certainly don't have a maximum or minimum, because that's what we're looking for, is whether or not we have maximum or minimum values. All right, so on this one, like you guys said, we needed to use, or we could use anyway, the quadratic formula. So somebody tell me, what's this going to look like? Everything's positive in this one, so that's kind of nice, actually. Over what was that, Taylor?
Over 2.
Yeah, over 2 times 1, which is 2. All right, so I've got negative 4 outside. Entire thing underneath the radical, what does that simplify to? About 8. Yeah, 8. I have 16 minus 8, so I've got 8. Square root of 8, that simplifies. Good. 2, square root of 2. Now you'll remember from either trig or an algebra course, because all three of these match, that is, they all have a factor in common of 2, we can reduce them all by dividing by 2. So we get a 2, a 1, and a 1 here. So this actually ends up becoming negative 2 plus the square root of 2, and negative 2 minus the square root of 2. And the only reason I write them out there is because I want you to recognize there's really 2 answers. Quadratic formula gives us 2 answers. Sometimes the 2 answers are matching exactly the same. It's a double root, but this one we actually get 2 distinctly different answers. So I have 2 locations where I'm looking at whether or not I have a max or a min. What did the directions say I could do on this one instead of the way we did the last one? Graphing calculator. Grab your calculator. And while you do that, I'm going to actually take this and I'm going to pause this video and we're going to look at the screen too together. Okay, so thinking in terms of number line like we did on the last one, we have 2 x values here. When I did my picture just a minute ago, I had something that looked like this. and it looked like this. This is not drawn well, but this was the point where we decided was our local maximum, or minimum, excuse me, this is our local maximum. We need to decide which of these x values corresponds to which one. This location right here, which of these two x values, negative 2 plus square root of 2 or negative 2 minus square root of 2, is the first of them?
Negative 2 minus.
Right. This is negative 2 minus the square root of 2. How do you know? How do you know this one's here?
That one's gonna be smaller.
It's going to be smaller because of the subtraction between them, right? And so then this is the negative 2 plus the square root of 2. So this one right here is the minimum value. So when we're writing our answer for this one, we have a local max at negative 2, or I'll say at x equals negative 2 minus the square root of 2. And we have a local min at x equals negative 2 plus the square root of 2. Now, I don't know about you, but on this one, I'm kind of thankful that they didn't ask me for the critical point. Because I don't really want to, although I could do it, right? I would have to put this numbers, which have square roots in them, and plug them back into that original function. And if they didn't ask me to do it, I'm not going to offer that option, right? So don't go and do more than you actually need to. They didn't ask you for that on this one. They just asked you for the x value, the critical number. All right, let's take a look at one other thing here. Local maximums are not the only type of maximums and local minimums. We also have things called absolute extrema. So absolute extrema really is the largest value. It really is the smallest value, okay, on a particular graph. Now, it may not be the whole graph. We may sort of limit what we're looking at our graph. So like when you look at a graph in your calculator, you're never able to see the whole graph. You guys know that, right? You always see a portion of it. That's why there's a y-min and a y-max and an x-min and an x-max. You always see only a portion of the graph. So we may be talking about an absolute maximum or minimum on a portion of a graph as well. So this is a point where the f of c value, just the location, is less than or equal to f of x. That means it is smaller than all of the f of x on that interval. That would be a minimum. Or it is f of c is greater than or equal to, it is the largest value on the interval. That's what an absolute extrema is. That would be an absolute maximum. The extreme value theorem tells us that if we have a continuous function, okay, that means it's all connected, and it's defined on a closed, bounded interval. So that means that it has a location where it starts, a location where it stops, and the endpoints are included. That's why you've got those brackets there instead of parentheses. Then it attains both a maximum and a minimum on the interval. This would be like the idea of saying, however many of us are in the room today, there's about 20 of us. If there are 20 of us in this room today and nobody else comes in or leaves, right, so it's a closed room, there's for sure someone, at least one person, who is the tallest person in the room. There's for sure someone, at least one person, who is the shortest person in the room. That's all this says, but it says it in terms of a graph. That makes sense, right? Yeah, I mean, you've got a graph, you've got to have a location where it's the tallest or a location where it's the shortest. And now the issue of it being continuous is really important because if it were discontinuous, like I had a hole in the graph, that'd be a problem because what if the hole in the graph happened at the top, right? So we don't have any of that going on. That's why we need this to be continuous for it to work. Now, actually finding these locations goes back to finding relative extrema. There are only two places on the graph where we could end up with the absolute maximum or the absolute minimum value. One place is we could talk about these peaks and these valleys, these relative extreme points. That is one location where we could find maximums and minimums. The other possibility is that we could talk about the end points of the graph. Like for instance, let's say that we had a portion of a parabola and because of where it stopped and started, this is the portion we had. Well, these 3 points are the 3 points that we would need to test to see which one's the maximums, which one's the minimums. So you'll notice that I didn't draw this very well because this is not quite in the center, but this point right here would be the maximum, right? It's the tallest point on the graph. Well, the two endpoints, one of them is the minimum because it's the smallest point in the graph. There's no way for any other location in between those 3 points, or differing from those 3 points, to be a maximum or minimum value. There's only two possible places where you can get maximum and minimum values. Relative extrema, which come from the critical points, and endpoints of the interval. So we're going to do one, and we're going to do one that's got a little bit of trig in it. It's a pretty straightforward function. We've got 3 cosine x. We have an interval that goes from pi halves to 5 pi over 4. And we're asked to find the absolute extrema. So to find absolute extrema means I have to test 2 types of points. I have to find those critical numbers and test them, and I have to use the endpoints and test them. And if you fail to test one or the other, you have failed to actually verify that you've checked all possible solutions. That's what you've done. So the first one we'll do is we'll do critical points, because I listed that first over here in the relative extrema. So let's do the critical numbers first. So to find critical numbers means to take the function and find the derivative, right? So what is the derivative of 3 cosine x? Okay, does everybody agree with that? Look good? After I find the derivative, what do I do when I'm finding critical points or critical numbers? Set it equal to 0. Now, in theory, I would also have to set it equal to doesn't exist, but I don't have that possibility here. Why? The sine curve, and sine curves always have function values. They don't ever not exist. All right, so now you have to put your thinking cap on with unit circle in mind. In fact, this whole problem is going to require some unit circle thought, so you might want to drag that thing back out in your mind. Where in the world on the unit circle is the sine value equal to 0? Because this happens at 0 and pi. Can you keep going? Okay, so how could you describe this if you were describing it and not want to write the dots? N pi. We talk about that in trig. This is all the whole pi values, right? Now, we don't need to test all of those values, do we? Just one. We are concerned with this interval, pi halves to 5 pi over 4. So the only values we test are going to be the values that are within the interval we're looking at, and there's only one of them. What is it, Blaine? Pi. So one of my test points, this is a test point, is going to be when x equals 0. Okay. I'm going to find some other test points before we test any of them. All right, so the other test points come from where? Oh, I'm sorry, I wrote the wrong thing down. Thank you. Yes, no wonder you guys are looking at me like I jumped off the moon. All right, so this is x equal to pi. Thank you. That's the test point that I get from the critical number. What else do I get? The endpoints, right. So I need to test the endpoints. So I also have my endpoints. So my endpoints are at pi halves and at 5 pi over 4. So I'm also going to do test those points. So what do I mean when I say I'm going to test these points? Well, when I test these points, what it means is that I'm going to figure out what in the world is the y value at that x value. That is, what is g of pi? And g of x was 3 cosine, so this is 3 cosine of pi. We're back to the unit circle, aren't we? What is 3 cosine of pi? Close. It's not 0. It's -3. Good job, Sam. All right, so what you want to remember with the unit circle is that we're over here when we're at pi, and cosine is the x value. The x value of that location is -1. So this is -3. So this is one of my y values to consider. Next one we're going to test is pi halves. So what is 3 cosine of pi halves? So pi halves is up here at the top of my circle. That's 0. Yep. The x value at that top of that circle is 0. Okay, the last one is 5 pi over 4. So I'm going to test 3 cosine of 5 pi over 4. Where is 5 pi over 4? Not third. Second quad. No, it is the third quadrant. I said the wrong thing. I'm sorry. Yep, down here. Yep, 5 pi over 4, so we're over here. So what's the cosine value there? All right, so I have negative square root of 2 over 2 times the 3, so I have negative 3 square root of 2 over 2. So these are the three y values that I am now comparing. The largest one is my absolute max. The smallest one is my absolute min. So what's my answer? What is my, let's do absolute max first since I said it that way already. Yep, the negative, is that one the absolute max? I think it's 0, right? The 0, although it's a small number, is the biggest number because the other two were negative. So we have absolute max, we'll say it this way, of 0 at x equals pi halves. What one's the minimum? The negative 3. Absolute minimum of negative 3 at x equals pi. So this is my minimum, and it came from the relative extreme points. This is my maximum, and it came from the end points.
Wait, why is it when x equals pi half and x equals pi?
Because that was the x value that gave us those values. So this absolute max of 0 right here
Oh, okay.
was when the x value was pi halves. And the absolute min was negative 3 when x was pi. Any other questions on that one?
How does the 0 play with these just there?
Ask the question again.
Our test points?
Yes.
One of them was 0. How does that play into the?
We didn't have a
not
test point of 0.
but
The 5 pi over 4.
Yes.
It's kind of like taking a look back at this picture. I had 3 test points, but one of them is not a max or a min. Right? This particular point was an end point, but it wasn't higher or lower than any of the others. It's just one of the 3 tested points that I had. And you may not have 3 points. I mean, you may have 6 points to test. You certainly could have more than just 3. I'm trying to think if you could have less than 3. You could have 2. 2 is the minimum that you would have because you'd have the 2 end points. So if you had no location between the end points where the slope was 0, you could have just the test the end points. That's a possibility. All right, we have one more question that we're going to look at. This is sketching a graph. So we're going to sketch a graph of a function with the following characteristics. It has an absolute maximum of 3 on the interval negative 2 to 2, and the absolute minimum does not exist. Now I want you to pause for a moment and read that really carefully. The extreme value theorem says that the absolute maximum and minimum always exist. So how am I going to draw a graph where they don't exist if this one says I always have them existing? What's the difference between the question we're looking at and the extreme value theorem?
Like a parabola that never ends?
Yes, it's the issue that it never ends. Notice that this says on a closed bounded interval. When it tells us that the minimum does not exist, it doesn't say it doesn't exist on the interval negative 2 to 2. Do you guys see that? It says it doesn't exist in general. So when I'm taking my graph, I think parabola is a great way to think about this one. Let me go ahead and draw the graph. I need to put in that negative 2 to 2 because that's actually given information about the interval that I am going to be working with. And I have to have a maximum of 3. That's a y value of 3. Now, you don't have to draw it in this way. I'm going to put mine right here. There is my maximum value of 3, and it is happening at an x value that is between negative 2 and 2, right? And I'm actually going to draw exactly what a couple of you suggested. How about a parabola? So on this parabola, and it should look a little bit more smooth than that. It looks a little bit jumpy up there at the top, a little bit sharp. But I have a slope of 0 at the top. In fact, I wouldn't even have to have a slope of 0. It just says it has to have an absolute maximum, so actually a sharp point at the top would be fine. And then it does not have an absolute minimum on the entire graph. Everybody good? All right.